Welcome to the lecture of set theory. So this is the first lecture in real analysis, and the topic is set theory and the types of functions. In this set of lectures, I will explain the concepts and also will solve the problems that will be useful for university exams as well as for competitive exams. Like for example, in competitive exams like GATE or different exams which are conducted as entrance for masters or bachelors, also GRE. These lectures will be useful. So let's start the lecture, set theory and types of functions. I will explain the concepts and also will, in the subsequent lecture, I will solve the problems based on this topic. So T is a mapping or a function from A to B. See, in set theory and real analysis, we will have a lot of notations. Please understand when I'm writing the notation and reading out, understand what does that mean. So here, T is a mapping from A. T is a mapping or a function from A to B. So in types of functions, first let us understand the injective function. A function it is said to be injective. So injective function is also called one-to-one function. So injective is also called one-to-one. So let me write the definition, then I will explain. Also, I will give sufficient examples so that everything will become clear. So here basically A and B are two sets, and it is forming a function from A to B. So the set A is called domain and set B is called codomain. So what does this definition implies is if T is injective, then if T is injective, then T of A1 equal to T of A2 implies. So here also the notation which is coming, please pay attention to this. T of A1 which is equal to T of A2. This symbol means this symbol denotes implies. This symbol means implies. So T of A1 equal to T of A2 implies A1 equal to A2. When I give the example, you will understand what does it mean. So T of A1 means A1 is an element belonging to the set A. So here A1, A2, these belongs to set A, and E1, A1, of A2 belongs to set. So this symbol means belongs to. When there is a belongs to symbol, that means A1 is an element of set A and A2 is an element of set A, because A1 comma A2 belongs to A. Similarly here T of A1, T of A2 are also the elements are the elements of set B. This is the first condition. Now the second condition for the function to be injective, that is different elements. These two conditions, if if these two conditions are satisfied by this function, then it is an injective function. So let's see an example. Now let me. Uh, I'm taking the first example here. I'm writing the elements of the sets in the each column here. So like x1, x2, x3, and y1, y2, y3. Here another element x4. Now let's check the A and B. So there is a relation between A and B, and that is the function. So let's not bother about what that function is, but rather that function is giving the um, elements like this. Now let's map like this. These two are mapped, and x2 is mapped to y3 and x3 to y2. Now here this function is injective or not. So how we can see that? Okay, let me put another element x5. Now let's determine whether it is injective or not. Now here T of x1 is equal to y1, t of x2 is equal to y3, and t of x3 equal to y2, and t of x4 equal to y4. So see the second condition, no two different elements in A, like no two different elements x1, x2, x3, x4 are mapped to the same element in B. So if here t of x1 equal to y1, and if t of x2 is also, for example, y1, then it would have been not injective, as it satisfies the condition 2 here and also the condition 1, because uh, if there is also there is also another element x1 and y1, and there will be a mapping, similar mapping, because of the function. So uh, y1 equal to y2 here, therefore t of x1 equal. So in that case, the first condition is also satisfied here. I will explain you where the I will explain you in another examples where the first condition would not be satisfied. Means an example where first condition may not be satisfied. Now let's take the second example. Um, we have a mapping like this. So in this mapping, you can see that T of x1 equal to y1, T of x2 equal to y2. Now here T of x1, so right, T of x1 is, sorry, this is T of x2 is y1, as you can see the mapping. Now T of x1 equal to T of x2, but this implies x1 not equal to x2 here. So the first condition is fa- failed, and no two different elements in A are mapped to the same element. So here two elements in the second example are mapped to unique element in set B. So this is not injective. Let's write here. We forgot to write. This is injective function. This is not injective. Now let me take example 3. Here two sets are real numbers. So the set 1 and set 2 are real numbers, and the function is defined as two x plus 1. Now in order to prove that, let's prove like this. T of x1 is equal to 2x1 plus 1 and T of x2 is equal to 2x2 plus 2x2 plus 1. Now from these two, by substituting x1 and x2, we can uh, get that if T of x1 equal to, let's write like this, T of x1 equal to T of x2 if and only if. So again the new notation, this one, it is if and only if x1 equal to x2. Hence, this is a uh, injective function. You have to use your intuition as well to understand things. This is all about the injective function. Now let's see about surjective function. Let me write the definition and conditions, and then we can see the examples. A function T mapping from A to B uh, is called surjective. Surjective function is also called onto function. If every element of the codomain B, if every element of the codomain B is the image of at least one element of the domain A. So in notation I am writing the same thing. The symbol is for every B belongs to this capital B set, there exists. Please see the notation for every B belongs to B. There exists symbol is this. A belongs to A, and this is such that these two dots represent such that T of A equal to B. So now we can write this. Sorry, we can read this as for every B belongs to capital B set, there exists element A belongs to set A such that T of A equal to B. Now, with examples, we will let's understand the surjective function. Let's take here example one. We have two sets A, B, X1, X3, X4, X5 are the elements of set A, and Y1, Y2, and Y3 are the elements of set B, and we have a mapping like this. Now, if we see here the definition, for every B belongs to B. So here we have three elements in set B, Y1, Y2, and Y3. For each element in set B, that is Y1, Y2, Y3, there exists a element in set A which belongs to A, set A. So that is X1, X2, and X3 are mapped here such that T of A equal to B. So we have here T of x1 is equal to y1, T of x2 is equal to y1, and T of x3 is equal to y2, and T of x3 equal to y3. So now let's see the condition of if every element of the codomain B, that is every element of the codomain B here is y1, y2, and y3. Um, there exists if every element of the codomain B is the image of at least one element of the domain A. So here it should be at least one element of the domain A. So for Y1 we have two elements uh, here, and for Y2 we have one element, and for Y3 we have one element. So this is a surjective. This is surjective function. But if you check whether it is injective or not, you can say that it is injective because T of x1 equal to y1 and T of x2 is also y1. Let's look at uh, x2. Sorry, example 2. We have two sets where the function is giving a relation between the elements of the two sets like this. Here we have elements, three elements x1, x2, x3, and in set B we have elements y1, y2, y3, y4. We have a mapping like this, and there is no mapping for y4. So now you can see based on the uh, definition. So for every element B in set B, so here y1 is the image of x1, y2 is the image of x2, and y3 is the image of x3. According to definition, each element must be at least image of one element in set A. But y4 is not the image of any element in set A. Therefore, this is not uh, surjective. Now here you can see, for example, y3 is image of x3, and there is no element in A for which the y4 is the image. Therefore, this is not surjective function. Now let's see the example 3. A function is mapped from, so basically the two sets are real numbers and the function is defined by, so we have to consider the case of all the elements that the real numbers compose, that real numbers include. P of x is equal to x cube. So now we have seen, now when we write set A and set B, whatever the elements in this we have, we will get cube of that, and that should satisfy this condition. Means we have to see whether it satisfies that conditions, and based on that we have to mention whether it is surjective or not. P of x equal to x cube. Now see real numbers. This is set B, and set A is also real numbers, and set B is also real numbers. So in set B, as it is real numbers, it can compass, it can include the elements uh, like plus positive and negative numbers. Let's not even go till that rational irrational numbers, but just let's see understand based on that real numbers include both positive and negative numbers. So let's say -8 is negative number, and 27 is positive number, and is -64 plus 64. Now uh, the set A, this also contains negative and positive. So here, for example, -2. When we cube -2, we will get -8. So this will form a mapping. And for 27, 3. And for -64, it is -4. And for plus 64, it is 4. Likewise, as these two sets are real, on both sides we get negative and positive, and each so now we have to check whether it is surjective or not. So for -8, I have -2. Like if whatever the value in set B, if I do, I will get some element in set A, because that is also real. For 27, I have 3. For -64, I have -4. For 64, I have 4. And for some other number, like for example, some rational number or irrational number. Suppose if I take an irrational number -5, it will also have some, when I do -5 cube root, I will get some value here. So there exists some value, let's say x. So like that, for every element B, as per the definition belongs to B, there exists some element A belongs to A in the set A. Therefore, this is a surjective function. Now let's see fourth example. We have a function which maps from set A to set B where both sets are real numbers. Basically, we can assume that these are A and B, but both sets are real numbers defined by P of x equal to x square. Now for this, let me write the two sets A and B, and the two sets are real numbers. Now, if it is set B, then which is real numbers, then it should have the elements both positive and negative. For example, should have like 2, -3, 6, something like 16, or as it is a, for example, -8. Because it is a real number, it can take any values like 5, -5. Now, if we see in the set A, so here it is like P of x equal to x square. So, but we know that x square is always positive. X square is always positive uh, for any value of x. For any value of x, x square is always positive. So that means set A contains roots like root 2 for this, and for this root 6. For 16 it is 4, and for pi it is root pi. Now if you see here, you can map root 2 to 2 and root 6 to 6, 4 to 16, pi to pi. But you don't have any element in A to map to -3. So as per our definition, for every element in set B, where B belongs to B, there exists A belongs to set A. But for -3, there is no element in set A that belongs. Hence, this is not surjective function. Now let's see the bijective function, third one. Let me write the definition, then we'll see the examples and understand. The function t mapping from is called bijective. is if it is both injective and surjective. Is on. Injective is also called one to one. So what does this mean? It has to be injective as well as surjective. This means that each element of B is the image of exactly one element of A. T is bijective if T of A1 equal to T of A2. This is a condition for which implies A1 equal to A2. This is a condition of injective. And it also has to be surjective. That is, for every B belongs to B, there exists A belongs to A, right in a proper lining, such that T of A equal to surjective. This bijective function, it defines a one-to-one correspondence between elements of A and elements of B. You can write in your notes. I can repeat once more. The function defines a one-to-one correspondence between elements of A and elements of B. We can write that as T of A equal to B. Only when this function is bijective, this condition will the inverse will hold. Now let's understand with examples. Example 1, we have set A and set B and elements x1. So we have a mapping from x1 to y1. So now first we have to check whether it is injective. If it is injective, uh, each T of A1 will be equal to T of A2, then A1 is equal to A2. So each element will have a unique mapping. So x1 has y1, x2 to y3, and x3 to y2, and x4 to y4. So it is injective. Now for bijective, every element in B should be the image of at least uh, one element in A. So here every element like y1, y2, y3, y4, each is at least image of one element. So y1 is image of x1, y2 is image of x3, and y3 is image of x2, y4 is image of x4. So each element is image of at least one element in A. So it is surjective, hence it is bijective. Second example. If Z represent the integers, so here two sets are integer sets, and the function is defined by t of x equal to x square. So integers means both both positive and negative numbers without decimal points. Now, if you take here A and B, A contains positive and negative, B contains positive and negative, but they all must be numbers without uh, decimal. So 1, -1, 2, 3, -3. I'm just writing in sequence, but like, just for mapping convenience, I'm writing like this. But now we have on the on this side, we have here also, as it is integers, we have positive and negative. So 1, -1, similarly 2, -2. Just writing in sequence. So now let's see whether it is injective or not. Now we have a mapping 1 to 1 because 1 square is 1. But if we take -1 root, as it is a integers, which is a subset of see, integers is a, this is another notation. This is subset of real numbers. So root of -1 we don't have in real numbers nor in the integers. Okay. Now for 2 we can write map to root 2, and for 3 we can map to root 3. But for -3 we cannot map. -1, -2, minus. Sorry, not. I'm just. I got. In integers we don't have this thing. Yeah. So for this we can map, but 2 we cannot map because square root of 2 is not present in the set A, as it contains only numbers without decimals. Similarly, for 3 we cannot map, and now see in the sequence 4 we can map to 2. And if you see here, you can map the -1 also to 1. -1 square is also 1. Similarly, -2 square is also 4. Now for now let's so this is the case, and these elements like -1, it is no, I am putting cross for whichever is not, whichever doesn't have, these are not mapped to any element in set here. Now here you can see two elements are mapped to one here. So for example, let me write that a1 equal to 1, a2 is equal to minus 1, but t of a1 equal to t of a2, which is plus 1, as you can see here. Imply a1 is not equal to a2. So this means that it is not injective. Now we have to check whether it is bijective or not. See, for bijective, every element in B should be the image of at least one element in A. Minus 1 is not image of any element in set A. 2 is not image of any element in set A. Similarly, minus 2, 3, even 5 is not. So here this is not surjective. So it is not bijective. Let's focus on example 3. It is defined by, so here both sets are integers, set A and set B. Now here also I have to take 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, 5, minus 4, and in B also I have to take positive and negative. So what I will do is I will take 1, minus 1, then I will just for mapping convenience I will take 8, minus 8. Similarly I can take 2, for example, any integer we may take, like 64, minus 27, 27, 3. Now if we see here, 1 cube is 1, minus 1 cube is minus 1, 2 cube is 8, minus 2 cube is minus 8, 3 cube is 27, minus 3 cube is minus 27, 4 cube is 64, minus 4 will be minus 64. But if you perform 2 power, then this is not integer. So straight away we can say that it is not surjective. Now whether is it injective or not? Yes, because for whatever the element cube root you find on this side, you will get unique value. Suppose 1 is 1 and minus 1 will be minus 1. So here T of A1 equal to T of A2 implies A1 equal to A2. So this is injective. It is injective but not surjective. Therefore, it is not bijective. Let's take example 4. Integers, and this is natural number set. Natural numbers are positive integers starting from 1, defined by x square. We have two sets. Now here there should be only positive integers which are greater than or equal to 1. So here I can write only 1, 2, 3, 4, 5, 6. Now on this side I can write only minus 1, 1, minus 2, 3, minus 4, 4, minus 5, 5. And here we have mentioned x square. Now we can map like, but we cannot map 2 to any number. 3 we cannot map because square root of 2 is not integer, square root of 3 is not integers, and 4 we can map to like this. 5, 6 we cannot map. Then after we can map only 9 to minus 3 and plus 3. So this is what, this is not injective, not surjective, not bijective. So based on this we can say that it is not bijective. Now let's take example 4. We have defined by t of x equal to x square. So here A, B we have. Let me write on B side 1, 2, 3, 4, 5. These are enough. And so let me write here. This is real numbers. So I can write minus 1, plus 1. I can write root 2. I can also write minus root 2 because these irrational numbers are also part of real numbers. Root 3 minus root 3, minus 2, 2, and so on. We need not go that far, just small amount of set is enough. Here we can map 1, 2, and so here each element of, so here T of it is not injective basically. Sorry, not injective. It was corresponds to one. But every element in B is mapping to one element in A, surjective. But since it is not injective, therefore it is a you can say it is not bijective. And we have example 5. Defined by t of x equal to x cube. So real numbers, and this side we have natural numbers. Here we have anything for that matter, 2 power 1 by 3, whatever it is, 3 power 1 by 3, minus 2 to the power 1 by 3. So I'm taking these elements just because like to show the mapping, or minus 3 cube root. So when we map, now 1th cube root is 1. So exactly it maps. Similarly, 4th cube root will map to. Similarly, 5 will also have. So here one element 1 to 1 mapping is there. So it is injective, and also each element in B, that is the cube root of each element in B, is found in the set A because the set A is the set of real numbers. So it is surjective. Hence, this function is a bijective function. Now we have seen these three types of functions: injective and surjective and bijective functions. What are the real world applications of these functions? One is in cryptography. Mathematics is very important for engineering and science, like physics mainly. So for physics and engineering, mathematics is very important. Even for computer, I mean, it is in computer science and engineering, mathematics is so much important. It is important to learn mathematics with dedication from the beginning. Like when you join the engineering, try to focus, try to have a solid focus on mathematics because it will play a vital role in your career. The second is sensor design. Third is control systems, computer graphics. In case of AI robotics, machine learning is totally dependent on mathematics. Mathematics has a huge implication in robotics, AI, and machine learning. So, in robotics, we need unique movements. In case of robotics, we need unique movements. So, this unique control of unique control of movements, it has implication of these functions. Okay? And also in signal processing and many other. You may also mention in comments like what could be the other real world applications. Thank you so much for watching this video. In the next lecture, I will solve uh, or give an example problem that will be a standard of some competitive exam. Thank you so much for watching this video. And please make sure to subscribe if you want to get the more lectures on mathematics.